Alright everyone, hello, my name is Giancarlo Mejia. I'm a senior in mechanical engineering and I'm the group reporter for group number 3 for the Rankine cycle experiment. So just an agenda for the presentation. We'll go over an overview of what the Rankine cycle is, how it works, and what the goals are. We'll explain the experimental apparatus. We'll also go into safety considerations for the procedure, as well as the raw data collected, some calculations to measure performance and other things, and then we'll draw some conclusions and uncertainties as well. So just a brief overview of the Rankine cycle. It was explained more in detail in the group lead presentation, so I won't go too much into it here, but basically uses water as the working fluid. There are 4 major components: a pump, a steam generator, or in this case boiler, a turbine that generates work, and then a condenser that changes the state of the working fluid back to a liquid from a steam. The idea here is that the pump takes the working fluid at a high pressure into the boiler turns the liquid into steam, the steam generates the work in the turbine, and then cycle starts all over again. But this is the ideal cycle. The purpose of the experiment is to gain an understanding of the actual cycle by measuring relevant data and calculating parameters for performance. So, picture of the experimental apparatus. There are a lot of moving parts here, but we'll only touch on the more important ones. That's the propane tank that provides fuel to the boiler to change the state of the working fluid. The turbine, which is here in the middle, generates power to the generator. And then the condenser tower, which turns the steam back into liquid, as well as the data computer for the MyDAX system to collect the data. So for some safety considerations for during the procedure, we want to ensure that the casters are locked. There are a lot of moving parts, a lot of high temperature parts, so we don't want those to move easily. We also want the front boiler door to be closed at all times. It should be obvious. The steam emission valve should be open when filling the boiler, then shut after. This is to ensure that water is actually getting into the boiler. Operating the boiler at not normal water level conditions could damage or potentially hurt someone. So during the experiment, we changed the volume to 4,600 milliliters as opposed to 5,500 mentioned in the manual. This is because standards from ASTM have changed for the boiler walls. The walls are now thicker, so the volume inside the boiler is less. There's a specific head that needs to be provided, but that's what we do to account for that. Inspection of the fuel source line. A smell or sound would be evident of damage or incorrectly connected. We don't want propane leaking during the experiment. We want to verify that the boiler pressure is positive within the first 3 minutes. This is to ensure that there is actually the correct amount of water. Once again, we don't want the incorrect level of water as to avoid damage, as well as not letting the water level reach below 1 inch from the bottom. For after shutting down, we want to close the steam emission valve. We want to verify that the red light is off. This indicates that there is no electrical energy to the burner or the blower. We also want to ensure that the fuel source is correctly turned off. So here, we're going to go into the raw data, the plots. The red lines indicate where I think steady state occurred. This was mostly based off the first graph, since during that time interval is the least amount of change in the boiler pressure. As we can see, it's not constant. This could be for various number of reasons that we'll get into later. But this is the temperature versus time. We have the turbine temperature and pressure versus time. We can see that at the inlet, the temperature and pressure are higher than at the outlet. Then we have voltage and amps generated over time, and then the fuel flow and the generator speed over time. Now for the calculations, we were tasked to pick one specific point within our steady state and pull these properties to do the calculations from. I chose it to do at 350 seconds into the experiment. These are the values that were at each point. Moving forward, for the boiler, I went ahead and calculated the mass flow rate of the system first, which was found to be 0.0049 kilograms per second. I then used it to find the rate of heat added to the boiler, which was found to be 12.9 kilowatts, and then the rate of heat from the propane to the boiler was 7.03 kilowatts. For the turbine, the work generated, or the rate of work generated from the turbine was found to be 0.155 kilowatts, and then the efficiency of the generator, which is the generator power over the work done by the turbine, was found to be around 5%. As for the condenser, the rate of heat leaving the condenser was found to be 12.8 kilowatts. The efficiency of the cycle was found to be 1.2%. Some conclusions: very inefficient system. The generator and the cycle are not efficient. Typically in industry, efficiency for a cycle runs about 40%. We also found these values, as mentioned earlier. Some uncertainties: the boiler pressure wasn't constant, could provide miscalculations or incorrect data, as well as difficulty maintaining voltage, amps. The load switch didn't seem to be working or have no effect on the equipment, as well as the lack of pump in the cycle. So, yeah, are there any questions?
Can you explain me the graphs? Because you just moved by saying these are the graphs, but there was no explanations. Can you go through that?
Yeah. I'm not sure what further explanation.
Like you explained the next slide. Can you go to the next slide? Yeah, you just said like we have the graph of turbine temperature versus time. You just mentioned bullet what, but just explain what your graph shows.
It shows that I mean, outside of the pressure and the temperature being higher at the inlet than at the outlet, I'm not really sure what you're looking for.
I am not looking for anything. I'm just asking you to explain one by one for every slide of like for every graph. Just explain me. If it's just one statement, just explain and go to the other graph. That's all.
Because there was no pump, right, generating or forcing water out of the boiler, and the condenser wasn't, the boiler pressure was not constant. Could be for a number of reasons, whether there's no pump or whether the water isn't being fed back to the boiler from the condenser. The temperatures seem to be constant. Probably due to the propane providing the heat source. The turbines seem to be working fine. The inlet pressure and temperature are higher than at the outlet. That's because pressure and temperature are lost during working conditions. As for the fuel flow versus time and the generator speed, it seemed like the turbine did enough to keep the generator speed constant. As for the fuel flow versus time, that's the fuel flow from the propane tank, and I don't really have an explanation for why it's sporadic as it is.